Yeah, the good news is I can take as long or as short as needed. So please stop me. It's a topic that is fascinating. And thank you for the award. It's a great pleasure to be here, especially receiving an award named after a pioneer in the field whose papers we read from 1970s and 80s, etc. I'm going to give you a history of the paper, but also a little bit of what's going on right now, because I think it's both fascinating and disturbing at the same time. The fact that this problem is not solved yet. Like after we wrote the paper, I told my students, this will be solved immediately. But right now, we're in a very different regime. So this is the paper that we're talking about. Unfortunately, none of the authors are here. Most of the authors are my PhD, master's, and bachelor students at Carnegie Mellon. Two of them were at Intel at the time, Chris Wilkerson and Konrad Lai. I will not name everyone over here. But we talk about RowHammer right now, and I use this analogy, this infrastructure. This is beautiful. If you get a bit flip, not so beautiful anymore. Another infrastructure, beautiful. If you get a bit flip, not so beautiful anymore. So essentially, another infrastructure that we're building today, this is Mr. Bean's infrastructure. And he's very happy, but if he gets a bit flip, he's not going to be happy anymore. So essentially, we're talking about bit flips. And RowHammer is the fact that you can predictably induce bit flips in commodity DRAM chips. And essentially, all recent DRAM chips are fundamentally vulnerable. And what's interesting to me is that this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you know of something else, please let me know. We'll correct this claim. And people are writing articles that look like this. This was in 2016. Let me give you the history of how we stumbled on this issue. So we were working on memory a lot. Memory is clearly an important thing in in computing systems. We were working on many issues in memory. And we were looking at scaling, technology scaling issues. As memory becomes denser, what kind of problems you will see. And we did some work, and this is an early position paper before we published the RowHammer paper. We always argued that these scaling issues are going to become much worse, and we should really think about scaling the system together with memory as opposed to just scaling the memory technology alone. I'll get back to this. So main memory consists of DRAM. Essentially, DRAM is a beautiful technology invented in the 1960s by Bob Dennard. You have a capacitor, and you have an access transistor, and you have essentially the access circuitry. And for this to work, all of these components should work reliably. Now, the problem is as you reduce the size of the circuitry, meaning that you want to have more capacity in your DRAM chips, all of these things start failing. And there's a lot of noise that happens. And RowHammer is an effect of this. Just to give you an idea, this is 2019 Samsung. This is what a DRAM looks like internally. The logical picture is very different from the physical picture. And DRAM manufacturers are actually doing a lot to etch these capacitors in three-dimensional manner so that you can actually get a lot of capacity. Okay, we were doing a lot of studies. This is actually, this is a study that we did with Facebook before RowHammer also. We found out that essentially, this was published in DSN in 2015 after some time. And we found out that essentially denser DRAM chips lead to a lot more errors in real data centers. And we really wanted to understand these things. So we built FPGA-based infrastructures. You're seeing the earliest one over here. I'm going to tell you why we really built it a little bit later to understand these issues. And more recently, this is where a lot of the RowHammer experiments were performed actually from the paper. And more recently, we open sourced it. Other people are using it. And there's newer versions like called DRAM Bender that are being used. So the real reason why we really built this infrastructure was to understand data retention issues in memory. So that was one of the scaling challenges that we believed was really important. I still believe it's important, but RowHammer is actually getting equally or more important. And these actually have a tension with each other in DRAM actually. So what is data retention? Basically, DRAM cell cannot retain data for long. You need to refresh it. And this is a problem in terms of performance, reliability, and efficiency. We wanted to get rid of these refreshes without eliminating robustness. So for that, you really need to understand how long a DRAM cell can retain data. And this is very much dependent on the process manufacturing variation. And if you really want to understand this, you really need to build an infrastructure to test the retention time of DRAM cells. Again, I'm not going to go into this. This is the reason we built this infrastructure. And we wrote papers about it. We are still writing papers about it. This is a tough problem. It's a beautiful problem, though. At the same time, we were actually doing a lot of studies on flash memory, SSDs. So we actually built this infrastructure, this is an FPGA-based infrastructure to test flash memory, to understand its reliability issues, robustness issues. And we were seeing a lot of read disturbance there. This is a paper from Dates in 2012, where we demonstrated some read disturbance errors. And we later wrote another paper to Intel Technology Journal, and we kept writing papers. I'm not going to talk about these. But essentially, these two things enabled us to think about, oh, what happens in DRAM? Is there some other error phenomenon in DRAM that could be sneaking into the DRAM chips? So several of my students were spending a summer at Intel in 2012. And even before that, we were collaborating with Intel on these scaling issues. And during the summer, we actually really intensified our efforts in the infrastructure. And we started doing some of these read disturbance studies in DRAM. And essentially, we found that existing DRAM chips are vulnerable. I'll give you the story a little bit. Basically, what's the problem? The problem is very simple. It's read disturbance. If you know memory, there's nothing new here. In the sense that as memory scales down, cells affect each other. Now, this should not be exposed to users. That's the key problem. Basically, you have, if in DRAM, you activate one row to access a cell, which applies high voltage to that row. And then you keep doing this repeatedly, activate, precharge, activate, precharge, activate, precharge. It turns out you flip bits in physically adjacent rows. Now, this should not be happening because you're just accessing that row over there, and you're not accessing anything else. You're not actually writing to anything in DRAM, right? Clearly, this breaks memory isolation, physical isolation. And those rows that get bit flips, the victim rows, as we call them, can belong to some other application, can belong to the operating system, can belong to some important keys, et cetera, important security infrastructure. And this is actually what makes it a real security problem in the end. It's a robustness problem in the end, which affects security, reliability, and safety. But security folks actually took away with the bit flips because they wanted those bit flips. If we get to it at the end, I'm going to actually mention some paper later on. Okay, so we tested essentially a lot of modules, 129 modules from 3 major DRAM manufacturers, and there are only 3 major DRAM manufacturers that occupy more than 95% of the DRAM market today. We'll name them later. We did ABC in the original paper, and we found out that more than 80% of the modules we tested are vulnerable to this problem. And we argued that it's a scaling problem. Basically, the test we did in 2008 or so, we could not induce errors on those chips where the cells were larger and far away from each other. On all of the modules that were manufactured between 2012 and 2013, we essentially saw errors. And the reason is basically as cells become closer to each other and as cell becomes smaller, this noise, this electrical interference becomes larger. And the number of activations or hammers to induce a bit flip reduces over time. So in older technologies, you could actually induce these bit flips, but the cells would get refreshed before you could actually induce a bit flip. Now, newer technologies, the number of activations to induce a bit flip was smaller than the number of activations you could actually induce within a refresh interval. So before the cells get refreshed, the bit flip happens. And we're going to talk about that in future if we get to it, if you have time. So please stop me if I'm running, because it's an exciting topic to me. Okay, I already said all of this. Why is this happening? There's electrical interference. There are very interesting device level studies. So this phenomenon was not actually well understood before our work. Later works actually investigated the device level mechanisms as well. This is actually fascinating to me also. People are still investigating the device level mechanisms. Okay, so if such a bit flip happens in a real memory system, now you have a huge implication on the higher level of the software because the data structures are immediately corrupted, right? And this could actually lead to a lot of issues. When we actually wrote the paper, we also released the source code, which many works improved on later. This source code is very simple. It's a user level program. What it does is basically it selects addresses X and Y, and hopefully they're in different banks. We did not do a good job in selecting the banks. There are a lot of later works that actually did a much, much better job than us. And basically, it bypasses the caches in the CPU, bypasses a row buffer in DRAM, and ping-pongs activations or hammers to X and Y. And if the chip is vulnerable, you will get bit flips. You could still try out the source code. I'd recommend trying out Google's, or more recently, Kaveh-Zyvi's source code on Blacksmith and et cetera, right? Okay, so we showed that on real Intel and AMD systems, you would get errors by running this user level program. Okay, so that's interesting, right? Clearly, we argued that this is a robustness issue. Let me give you the history a little bit going forward as well. So the first people who really picked up on our work were testing people. This is Passmark software, MemTest 86. You may have used it. These folks actually included a version of our program in their tests. and it's test 13, hammer test. And immediately, they started getting inquiries from people saying that, oh, we're getting errors in DRAM. Why is this happening? And they had to write on their website that the errors detected during this test 13, albeit exposed only in extreme memory access keys, are most certainly real errors. So, and then they have some other stuff in their website that's interesting. So when we wrote the paper, the first sentence, and I still believe that this first sentence we should satisfy, is memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. We said that we should maintain this, and I don't think we should go back any time on this one. We also said that someone can take over your system if by taking advantage of these Bitflips. We did not demonstrate that, but we demonstrated the proof of concept of Bitflips in a real system. The other people that took on our work initially was Google. Google Project Zero basically read our paper and replicated the results, and they were basically able to devise an attack that would take over the Linux kernel using these Bitflips. I'm not going to go through this, which is very, very interesting. It's beautiful black hat presentation that they have. This is actually copy and paste from their blog post. They were able to induce Bitflips in the page table entry of this user level program such that they would actually get access to their own page table, meaning write access to their own page table. Once you have write access to your own page table, all bets are off at that point, right? So this became famous as the RowHammer vulnerability, especially after this Google paper, and people started writing things like this. Like this is a famous hacker saying, it's like a RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. I like this one. Hackers are actually quite insightful in explaining things, I think. There's a whole line of security work, in my opinion, that were waiting for these Bitflips, meaning they wanted to have these Bitflips with real software so that they could actually show what you can do with these Bitflips. Clearly, theoretically, it was very well known, I think, that in the 1990s, if you have a Bitflip, this is very bad for cryptography, right? You could actually lose all your keys, etc. But RowHammer enabled people to actually test this in real life, let's say. And again, I won't go through these papers. There are a fascinating set of papers in the security community, including DSN, that talk about these attacks. I'll just mention them. I will mention this one. This is interesting because RowHammer is an integrity problem. But even if you may not be able to take over a system by compromising integrity, you could actually access data that you're not supposed to access to. So these folks actually turned it into a confidentiality problem as well, which is very interesting. So RowHammer as a side channel was shown by this paper. More recently, people have shown that you could actually corrupt neural networks, etc. And Google and Microsoft have been doing work on this also. If you have time, I'll get to that as well. And people have been drawing pictures like this. This may be a solution or an attack. Okay, we've been writing a lot of papers. I will not talk about some of these. So what our paper did, I think there are two major things, understanding and solving the problem. Our paper did both, and I think it's really necessary to do more of this today. So that's why we built this infrastructure. We tested a lot of modules, and we showed that by understanding the problem, you can devise better solutions. Again, I will not go through these. These slides are meant to be reconfigurable. You can, I'd be happy to share them, etc. But by reducing the accesses to DRAM, you can reduce the problem. Not a good idea, bad performance. By refreshing DRAM more frequently, you can get rid of the errors. Not a good idea, because we wanted to get rid of refreshes. Remember, that's why we built this infrastructure, actually. And in fact, our paper showed that if you want to get rid of every single error in every module that we tested, you have to increase the refresh rate by 7x. We're going to get back to the solution. Data pattern is has a huge effect on the errors that you see because it affects the charge coupling and the noise. And there are many, many other observations I'm not going to talk about, but I'd be happy to talk about separately. So more recently, a lot of people have improved on this. So we're actually investigating RowHammer. It's getting much worse. It has many dimensions. It has a lot of interesting interactions. And a paper was presented yesterday by Ataberk on HBM chips. HBM is actually critical infrastructure today, and RowHammer is as bad, if not worse, in HBM chips today. Okay, let's talk about solutions, because solutions are necessary also, right? And this sort of issue discovered in the field, you have to have solutions immediately. Now, unfortunately, we didn't have a lot of leeway in real systems because memory controllers were not programmable. That's what we're going to argue soon. Longer term solutions could be actually much better. So our paper proposed 7 different solutions. One of them I'm going to mention, and then I'll give you a history of what happened to that solution. So there are actually many solution approaches. A lot of them actually we discussed in our paper. Unfortunately, there's no easy way to solve this problem today for the reasons that I will discuss. And all of the solutions are a trade-off between cost, power, performance, complexity, and hopefully not robustness. Hopefully, we don't want to give up robustness in the end. Now, you can combine different solutions in different ways also, and different solutions that has upsides and downsides. So what did people do in industry? Essentially, industry increased the refresh rates because that was the only lever that you could have in a memory controller. And this is Apple. I like Apple because they actually reference our paper when they actually released their CVE. And they basically said that this issue was mitigated by increasing memory refresh rates. They didn't say how much, probably 2x. And that's not enough to get rid of all of the errors, by the way. It closed the vulnerability, but we're going to talk about that. So our solution was probabilistic. We called it PARA, probabilistic adjacent row activation. With very low probability, when a memory controller closes a row, it activates one or more rows. And this actually gives you a very good reliability guarantee. And if you're paranoid, you can adjust the value of P. And we analyze the solution. It's low cost. It's still the lowest cost solution. We said that you could actually implement it in DRAM chip or the memory controller. It's done today in both. It was actually adopted by Intel very early on. They basically, this is a BIOS screenshot where you can see that you could pick your RowHammer solution. You could pick hardware RowHammer protection or 2x refresh. And if you pick hardware RowHammer protection, you have a choice of probability. How do you reason about that? Good luck. You don't want to probably activate a row every other activation, right? Okay, that was not exactly how we envisioned it, but it was a step in the right direction, in my opinion, actually. Okay, so there's more RowHammer solutions proposed. So I think this is an example of an intelligent memory control, slightly more intelligent, that's trying to fix the problems. And we always argued that we have actually memory controllers in Flash, and we have a lot of intelligence over there. Our argument was that in DRAM, we should have more intelligent memory controllers also to fix these issues, because these issues aren't going to happen in the field more and more. And okay. Now, let me give you the history of what happened a little bit, because I think it's really important to see where we are today. Intel was developing solutions. I think AMD was developing solutions. But at some point, DRAM manufacturers said, we solved the problem. And everybody believed that. So we questioned this. I'm going to give you very quickly what we've done. We actually analyzed, revisited RowHammer 6 years later, the Saniska paper 6 years later. And we tested even more chips, many more generations, 1,500 chips. And we showed that this is actually a very difficult problem to solve. Meaning, newer chips are more vulnerable because cells are closer to each other. You get bit flips after only 4,800 hammers. And existing mitigation mechanisms are not effective, basically. So we built a lot more infrastructure. And this picture shows that from left to right, you're marching towards a smaller number of activations that could induce a bit flip. This is the latest generation chips that we tested. And mitigation mechanisms actually become much worse in terms of performance and energy overheads, as you can see over here. Okay. So basically, RowHammer is a technology scaling problem, and finding a good solution to RowHammer is difficult. So, and will become more so. I don't think this problem is easy to solve. Actually, you can actually see interesting numbers of how many activations you need to do to induce a bit flip. We're marching towards almost 1. And at that point, DRAM may not be scaling, and maybe we should really do something else. Okay, so we also wanted to understand what kind of solutions did manufacturers put in, because they were actually relying on security by obscurity, meaning that, oh, we solved the problem, trust us. We basically said, can we actually reverse engineer what's going on in existing DRAM chips and bypass these mitigations? And that's essentially what this work did. Basically, the solution was like this. If you want to induce a bit flip, you just figure out how to induce the bit flip. That's the idea. So internally, DRAM manufacturers introduced some tables, and we reverse engineered them. And we devised access patterns to overflow the internal tables that would count the activations to different rows. And we were able to induce bit flips in real DRAM chips by using attacks that look like this. So instead of having 2 rows that you hammer 4 rows. In some chips, you need to hammer 7 rows. In some chips, you need to hammer 9 rows. But you would overflow the internal protection mechanisms, and then you would induce bit flips. And we kind of declared victory, showing that, oh, you could actually induce these bit flips on real phones, etc. Basically, I think this still, I would still argue that this is important. This is true. Basically, we don't want security by obscurity, I think, going forward. Unfortunately, I'm going to show you the solutions that are adopted today. We're at the same point. Manufacturers are still relying on security by obscurity today. Okay, so these works actually cause a lot of churn in industry, and they basically JEDEC finally started taking the problem much more seriously. And they basically induced these two papers. They published these two papers. And more recently, the standard, DDR5 standard is updated. I'm going to mention what solution is that. But basically, if you have an infrastructure like this, you can completely reverse engineer what's going on in DRAM. I'm not going to talk about this. You could actually do much worse. I will mention the industry effort also, because this is actually really interesting. Google, Microsoft, and some other industry took a lot of interest in this work. Google actually showed that in 2021, you could do RowHammer far away, meaning if you have a far away aggressor row, you could actually induce Bitflips in a victim that's far away, which is interesting. I'm not going to talk about the implications of it. Microsoft also wrote papers saying that you could actually do this in real workloads, commodity workloads. Okay, I'm almost getting to the end. Okay, this is interesting, I think. And these folks actually were perhaps the major drivers in pushing manufacturers to do something better. We'll see if they're doing better. So we always argue that you need better memory controllers. There are a lot of work in this area. And I still believe that we need better memory controllers, better programmability in the memory controllers. Okay, let me talk about what industry is doing right now. So this is 2023. This is the first paper from industry, SK Hynix, which is a major DRAM manufacturer, second biggest one. This is the first paper that acknowledges RowHammer. It uses the word RowHammer. And they basically introduce an intelligent memory controller in DRAM. I'm not suggesting this is the best solution. What they do is internally inside the DRAM chip, every single row has an activation counter. And these activation counters are incremented when a row gets activated. And they take some mitigating action if the activation counter of a row is greater than some threshold. They don't disclose how exactly this works. They claim they reduce the RowHammer vulnerability. So it's more security by obscurity, again, in my opinion. Samsung actually, after seeing the SK Hynix paper, he wrote a paper too, but this is a mess. Okay, and there's a paper coming up in DRAMsec that shows that it's kind of a mess. Okay, Microsoft actually proposed a solution like this earlier than SK Hynix. And this solution is actually adopted by JEDEC in the recent standard, DDR5 standard. This is April 2024. They call per row activation counters. We have an analysis of this coming up next week at DRAMsec showing that this is actually vulnerable to denial of service. It may actually fix bit flips depending on the conditions, but it may not be very good for performance. Okay. So basically, I think that's a good question to ask. Are we now RowHammer free in 2024 and beyond? I don't believe so. And I think there's a lot more that's going to come up soon. Since we don't have a lot of time, we've shown last year that you could actually induce bit flips by keeping a row active, a single row active for a long time. This is called RowPress. And this is very different from RowHammer, it turns out. Basically, this picture shows the example. RowHammer, you keep activating a row many times. RowPress, you keep the row active for a longer time. And you get bit flips at much smaller hammer counts, less than 1K today. Okay, again, I'll skip some of these over here, but you can see that we're marching towards very small hammer counts where benign applications are actually inducing these bit flips almost. I believe there's more to come. So I think we need to do more in this area. We need to understand more and we need to solve the problem more. And there are a lot of works that are going on right now that I will kind of flash at you over here. So these are some of our works. But there are other works also. These are actually a collection of the works that a small collection of the works that I've been looking at this year in different conferences, as you can see. And there's actually a DRAM security workshop that has a bunch of RowHammer papers. I just looked at it yesterday night. If you're interested, you can take a look at it. So people have been actually doing these attacks on RISC-V. And Google has a paper actually showing that Samsung solution is not good enough, which is really interesting, as you can see. Okay. So what about the future? I think future is much more bleak. Basically, we're marching towards a much worse regime as technology scales, and we need to think about our systems in a better way. Okay, let me go back to the bridges. I'm going to end. So people have been building bridges for thousands of years, right? And we still have bit flips in bridges. Some of you may remember some of these things. This is close to my heart. I used to be at CMU, and this bridge I used to go over, and then it collapsed. So we haven't figured out how to build bridges, but I think we have a better shot at computing infrastructure, hopefully, by having intelligent memory controllers. I think this is the place I'll stop. I'd be happy to talk more, but I'd be happy to take questions also.
Okay, there's a mic over there. You can go. One of you can start and then get around. Go ahead.
Thank you for a very interesting, inspiring talk. So I had two questions actually. So one is you mentioned that memory isolation is a very important property and we don't want to go back on that, right? But it looks like the more we try to preserve that property, the more cans and worms in the can there are. So I wonder if we should actually rethink this abstraction and start building software level solutions that can deal with these kinds of memory errors. And in this community, there's a lot of work that tries to build other kinds of solutions than just pure hardware ones to deal with these problems. So what are your thoughts about that? And secondly, have you thought about extending these to CPU kind of faults, especially in light of the new SDC causing errors that Google?
Yeah, thank you, Karthik. Both are great questions. I think the first thing is absolutely. I think we should really preserve the memory isolation abstraction at any level that we can actually preserve it in a nice way. It doesn't have to be done completely in hardware. In fact, it's going to be very, very difficult to do that completely at the hardware level. We need to think about different ways of potentially writing the software. The difficulty is, of course, it's not easy, right, for the software to handle that. And the overheads may be very large. But that's the system level solution space that we really need to explore, especially if this problem doesn't get solved. The second is, yes, I think SDCs are another example of hardware errors, Bitflips. In fact, one of my slides, I generalized the hardware Bitflips, and we should really take them seriously also. The solutions over there are going to be, I think, in my opinion, different, because I think solutions in memory are different. But in the end, some principles are similar. If we, for example, have more flexible hardware that would test itself over time and figure out these issues while it's in the field, as opposed to putting a huge burden on the manufacturing subsystem where we actually spend a lot of money, etc. That would be very useful. If we configure the hardware to fix some of these issues online, I think that can be very useful. So there are some solution approaches that are similar with SDCs and RowHammer.
Thanks for a very entertaining talk. There's a shocking takeaway from all this, which I guess I alluded to yesterday already, that the hardware manufacturers were caught without hands down, violating blatantly the hardware-software contract. When it got pointed out to them, they ignored it. In political concourse, that's basically called shifting the overtone, where we now accept that there is the hardware-software contract gets violated. How can we ever get back to that? Because now there is the president. You can just ignore this. People will live with it. And we cannot possibly build secure systems.
Yeah. Yeah, I mean, you have a very good point. And I was at your talk. I enjoyed it. I agree with you that they should not have ignored it. They should have taken it more seriously. Can we get back to it? Meaning, right now you have these Bitflips, and can we somehow really get back to a place where we can say, okay, you're responsible for fixing it, fix it, and don't. I think it's tough. It's tough once that thing is broken. I think that's why I think we really need to, in my opinion, we haven't found out the partitioning of responsibilities between memory and the memory controller. Right now, memory is manufactured by some hardware vendors. Memory controllers are manufactured by some other hardware vendors. And that's the interface is broken, in my opinion. And as a result, a lot of the solutions are hampered. So if some of the responsibility was actually given to the memory controller inside the DRAM, and they could have some freedom to do things, in my opinion, we could get back to that. So I think that interface is broken. Yes. Now, that's a great question also. So if the numbers are less than 1,000 activations per refresh interval, there are a bunch of applications. Actually, many applications do that. If the numbers are higher than that, in fact, there are some applications, and the Microsoft paper that I mentioned showed that. For example, if you are able to induce 300 Bitflips with 300 activations, many applications do that actually today. So it's a very general purpose problem, let's say, in that sense. But some applications, when we were doing these studies, actually, we actually had a lot of interactions with industry as well. And there were some applications, some benign applications that induced Bitflips even at that time, even when you actually needed to do 100,000 hammers to induce a Bitflip. So what is that sort of application? It doesn't do caching, meaning it does a lot of non-cacheable memory accesses. And it hammers on a row. You can imagine that if you're trying to get a lock in a row and there are many threads banging on that lock, you could actually be doing that sort of hammering. And one of the applications was like that.
Okay, thank you.
Okay.
So we don't have much more time.
Sorry.
Onur,
Oh.
this is your.
Okay. Thank you very much. Thank you. Okay, thank you.
Presentation.
Sure.
So before